So if an operating system can create a process and can switch from one process to another, then it can have as many processes as it likes, as long as the total amount of state and data for those programs fit in memory. And actually, as we'll see in future videos, it doesn't even need to have enough memory to fit all of the programs. It really just needs to have enough memory to fit the one that's running currently, and really only parts of that program, the ones that are actually being used frequently. We'll get into more of that when we talk about virtual memory. But for now, the key thing we want to know is that we have a process abstraction, the ability to represent a single instance of a program that's running. And we're able to switch. So we're able to switch from A to B to C to D. So here we have 4 processes, A, B, C, and D. There's just one program counter, just one CPU, but the operating system is able to run A for a while, then switch to B, then switch to C, then switch to D, switch back to A, and switch to any process that it wants to run. The operating system needs to keep track of how many processes it has. It needs to keep track of A, B, C, and D. If it does that, and it does the switching, then a single CPU over time can run many different processes. It can run A, which it runs for this period of time. It can run B, which it runs here and here. C, as we see here, ran at this time, and D ran at this time and this time. None of these programs are actually running at precisely the same time. Instead, they're time sharing with the CPU. Each one gets a period of time with the CPU, here, 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 there, 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 and there. And then each one does its calculations until the operating system decides to stop that process and to run another process. Call this multi-programming. Multi-programming of these 4 programs in the same physical memory. And it gives us a conceptual model, both here, here, and here, gives us a conceptual model of 4 independent sequential processes. They don't know about each other. They don't conflict with each other. They just happen to time share the hardware, thanks to the operating system. And only one of them is active at any one given instance. So then the next question is for the operating system as to which of these processes should run at a given time. And that's the job of the operating system scheduler. The scheduler has many processes here. We show it has n processes. Then it's up to the scheduler in the operating system to decide which one should run next. This is the lowest layer of a process structured OS. It's the most basic functionality of an operating system, to schedule processes. It also needs to handle interrupts from external hardware devices, and it needs to schedule processes. Processes then, the process abstraction exists above the scheduler layer. Processes then can be in any number of, well, in one of 3 states during their lifetime. And this diagram here is an extremely important diagram that I want you to be able to understand and analyze and use. So I'm going to go through it in fairly amount of detail right now, and then you're going to have more practice with it in our assignments and in quizzes and exams that follow. There are 3 states. One is the block state, meaning the process is not running for some reason. One is the ready state, meaning that it's ready to be run. So I should have said in the block state, a process is blocked, it's waiting for IO, it is not yet ready to run. When it becomes ready to run, it then goes into the ready state. And then of all the processes that are ready, one of them is chosen by the operating system to be in the running state, which means it's actually running and using the CPU at that time. The transitions between these states are shown with these 4 arrows and listed over here. As a process is running, if it does an IO, and it needs some data, say from a disk or from the network or from a keyboard or a mouse or something, it will stop and go into the block state and wait in the block state until the input completes, whatever input it's waiting for. So this is sometimes called the waiting state as well, but for now we'll call it the block state. So a process is running, it needs to do an IO, that is transition number 1, it goes into the block state. Transition number 2 is that a process is running and the operating system just decides at that moment that the process should not be running anymore. It makes a scheduling decision, a resource management decision, and decides that the current running process should be moved to the ready state and a different process should be moved to the running state. Transition number 3 occurs when the operating system decides that one of the processes, one of the many processes in the ready state, is now supposed to run according to its scheduling algorithm, and it moves that process from the ready state to the running state. That's transition number 3. And finally, transition number 4 occurs when an IO operation completes, whether again it's a mouse, a keyboard, a disk, some other CPU, or a network packet arrives, then the process goes from the block state and transition number 4 into the ready state, meaning the IO for which it was waiting has occurred and the process is now ready to run. So please look at this carefully. Please understand this diagram carefully because it's something that's going to come up over and over again in the course.